System, we say, is in a state of equilibrium. If it's not changing, all of its properties are well defined. Okay, so there's no changes that you're seeing in your system. And so equilibrium basically is what we're saying is the ultimate fate of all processes. Eventually everything stops, reaches equilibrium. So how do we define actual equilibrium from an operational perspective? You can say that a system is at equilibrium if it's at thermal equilibrium. There's actually three conditions it has to satisfy. It has to be at thermal equilibrium, it has to be in mechanical equilibrium, and it has to be in material equilibrium. So there's three conditions that must be satisfied for us to be able to say that the system is at equilibrium. So what does thermal equilibrium mean? We say that a system is in thermal equilibrium if its uniform is constant and uniform throughout and it's not changing. Okay? So if you're allowing energy to flow between your system and your surroundings, then your system must be in, we say, it's in thermal equilibrium with your surroundings if they are at the same temperature. Okay, so if your system and surroundings are at the same temperature. Now, if your system is separated from the surroundings by adiabatic walls, the word adiabatic walls means it's thermally insulated. So if you're not letting heat flow between your system and your surroundings, then you say your system is at thermal equilibrium if the system itself has a constant temperature, okay, and that temperature is uniform throughout the system. Mechanical equilibrium. When is mechanical equilibrium established? If the volume of your system is not changing, okay, so that means the walls are not moving, it's not expanding, it's not contracting, its volume is fixed, then we say it's at mechanical equilibrium. What that means is, so if you have a system right here, okay, at the boundary between the system and the surroundings, the force per unit area that the wall is experiencing from the system side would be equal to the force per unit area that the wall is experiencing from the other side. So it's getting equal push from both sides, so it's mechanical equilibrium. It's not going to move, right? So if we define P, the force per unit area, as the pressure of the system, and then the force per unit area from the outside would be your external pressure. So what happens when those two are not equal? Then we say we're not at mechanical equilibrium. Your wall is going to move, so you either squeeze your system, okay, or your system will expand, okay. So when will it, in what case will your system be squeezed? When the pressure outside is higher, okay? And when will it expand? If the pressure inside is higher than the outside pressure. Okay? Material equilibrium happens when your system's composition is fixed. That means there's no more chemical reactions going on. All chemical reactions have stopped. Every substance that's present in your system will have a fixed constant amount if it's at equilibrium, at material equilibrium. So no net chemical change, and there's no net phase change. You're not seeing any solid turning into a gas or gas turning into solid. So it looks like everything has stopped. It looks like there's no changes there in the composition of your system. So in that case, you'll reach material equilibrium. Of course, we know at the atomic level, okay, processes actually continue to happen because atoms and molecules are constantly moving. So even if we see a reaction appearing to have stopped at the atomic level, it hasn't really stopped. It's just that reactions are reversible. So if you have reactants colliding to make products, products will collide back to make reactants. And chemical equilibrium is, we say, is established when the rate at which the forward reaction is equal to the rate of the reverse reaction. But thermodynamics is really concerned more at the macroscopic level. That means what we can see from the outside, not at the molecular level in terms of the concept of material equilibrium. Okay? So material equilibrium actually is what we might call a dynamic equilibrium because at the atomic level, nothing has really stopped. It just appears as though it stopped because you got two opposing processes, one going forward, the other going in reverse.